This is the thinnest, fully working redstone computer in Minecraft, completed with RAM, pixel display, speakers, controller, and random number generator, while being just one block thick. Hi, I am Pumik, and today I want to show you my most complex redstone build yet, and explain why I made it, how I built it, how it works, and what programs you can run on it. In recent years, many tech companies have been trying to make their products as thin as possible, particularly laptops, smartphones, and tablets. However, this wasn't always good, because a lot of times it caused problems with cooling, battery life, and repairability. And that is why I decided to do something similar in Minecraft. I knew from the beginning the computer won't be faster or better than those before, but I thought this would be a fun challenge. The practical limit in Minecraft is one block of thickness, so that's what I aimed for. And no, I am not counting support blocks beneath the redstone, as they don't influence the circuits in any way. Here I used barrier blocks as the support, so it looks like it is truly one block thin, that I am not hiding any redstone below. Most computers use binary, ones and zeros, as a means of data storage, and logic gates, small, simple circuits used for computation. Both can be easily built with redstone, even with the one block height restriction. However, the biggest problem I had was how to cross redstone wires without any interference. My first thought was to use calc sensors to send data, but they are too slow and output a short pulse instead of a stable signal. So I started searching on the internet and found a couple solutions. First one, that was on the smaller side, uses cleverly placed XOR gates to swap two redstone signals. But it wasn't very fast and its size made it inconvenient to use. Another solution was to use droppers and hoppers and the fact that comparators can read how full containers are through a full block. But it still wasn't good enough. It takes 3 redstone ticks to power it on, but just 1 to power it off. This inconsistency was harder to work around, especially when building a computer where every component needs to be timed perfectly. During my search I found this video by Rubik's Terra, where they explain different ways to cross redstone wires, not just binary but also hexadecimal. And in the middle of the video they said this.
But even aside from that, as impractical as these kinds of circuits may be, their very existence definitively proves that crossing wires is never necessary for logical redstone, no matter how complex the goal is. That said, it makes no claim as to how simple that alternative may be, but also just the fact that you could theoretically make an entire processor in just one layer of redstone is kinda mind-blowing.
Well, that's exactly what I've done. But I still wasn't satisfied with the way I should cross redstone, so I moved to a different part of the internet, Discord. Particularly MadBadWing's server called Redstone Army. And there I found two solutions that are both tileable in 4x4 blocks grid and take 2 redstone ticks to power on and off. But when I looked closer, I realized that it can be improved even more. And this is my final version of redstone intersection. It is tileable in 3x3 blocks grid and has just 1 tick of delay. The way it works is that the signal entering the crossing in one way is the maximum possible strength, 15, and then is captured by this comparator in compare mode, comparing it with a strength of 15, going to it from the side. And the signal going in the other way has to be 14 or lower and sent to the other side using a comparator. Because it is lower than 15, it won't leak and will go straight through. The signal values can be modified in the barrel. So if there are, for example, items producing signal strength of 13, the signal going one way has to be 13 or higher, and the signal going the other way lower than 13. The barrel can be also replaced by a redstone torch and a repeater. Side note, I believe it is possible to build a true one block thin computer which doesn't need any support blocks, using pistons, redstone and slime blocks, observers and calc sensors, but I haven't looked into it too much. And with this done, I could start designing the computer. I decided to make my computer 6-bit, which means it works with 6 bits at a time, that can represent 2 to the power of 6 or 64 numbers. number 0 to 63. This is called word size. The word size in most modern computers is 32 or 64 bits, thus it can represent far more numbers than 6 bits. But I thought this would be appropriate amount for my computer. There are multiple types of CPU architectures, but I went with so-called load store architecture. It has a small number of registers, memory addresses with quick access that take part in every computation, store both the inputs and the result. Besides that, it has many memory addresses, which can't be used directly for the computation. Instead, the values in them have to be written into registers and vice versa. So the memory is big and slow and registers small and fast. Lastly, I decided for a fixed length for every instruction, 12 bits. First 3 bits tell the processor what to do. They are the operation code, or opcode. The rest is usually divided into 3 groups of 3 bits. Each one of them is an operand, typically a register address or some additional information about the operation. Because the opcode is 3 bits, there will be a total of 8 different instructions for the CPU. Now I could start building the computer. With each new component built, I will add new instructions to this table. First component I made was this register file. It has 8 registers, each of them can store 6 bits of data. The only exception is register 0, which is basically non-existing. You can read from it number 0, but every attempt at writing to it will be voided. However, it is very useful when comparing values or resetting other registers. All data in registers is stored in duplicate, so you can read from 2 different registers at the same time. Contents of each register can be seen on these redstone lamps. Here are the inputs, the 6-bit value, write signal, reset toggle, and a 3-bit register address. On the sides are 3-bit register addresses for reading from the memory. I can, for example, write a number 5, 101 into register 3, 11, and number 11, 1011 into register 6, 110. Then I can simultaneously read from these 2 registers and see the values on the other side. The second component I created was an ALU, or Arithmetic Logic Unit, where all the computations take place. As the name suggests, it can perform arithmetic operations, such as addition and subtraction, and logic operations like bitwise XOR, AND, OR, and other. On top of that, it is capable of bit shifting to the right. On one side are the inputs, called A and B, and on the opposite side the output, called C. It has 2 additional 1-bit outputs called flags. I will talk about them later. These levers change the operation the ALU performs. The design is heavily inspired by Mad Bad Wings and the ALU he made in his series How to Make a Redstone Computer from Scratch. So if you want to know more, definitely check that out. Just to show how it works, I can make it to do math. Let's say we want to compute 10 minus 7, so I input the correct bits. 10 is 1010 and 7 is 111. Then I turn on invert B and add carry in, which are the control signals for subtraction. The output is 11, which in decimal is 3. With these 2 main components, I can add some instructions to our table. First instruction with the opcode 000 is addition. It has 3 operands, addresses of 3 registers. The first one is a register where the sum gets written into, and the other 2 are registers that get read and the values in them are added together. Second instruction with the opcode 001 is subtraction. Works very similarly to addition. I will skip the third instruction for now, but I will come back to it. Next 2 instructions are bitwise AND and exclusive OR. The 6th instruction is bit shift to the right and has the opcode 101 and has slightly different operands than the instructions before. The first 2 operands are the same, but the last one isn't an address. It is a further specification of the instruction. If the first bit is on, the ALU will perform rotate instead of normal bit shift, where every bit that would disappear on the right is now moved all the way to the left. And the last 2 bits tell the ALU by how many positions it should shift the number. Minimum is 1 and maximum is 4. To be able to run programs, we need a place to store them. That's the purpose of program memory, another component of the computer. This one can hold up to 126 instructions long program, with instruction 0 and 127 reserved. Each instruction, as I already said, is 12 bits, so the total capacity is 1512 bits, or 189 bytes. The current instruction that is being executed can be seen highlighted using a redstone lamp beside it. Instructions have to be inputted manually by placing or removing redstone dust to and from these spots. Redstone dust is 1, almost anything else is 0. Instruction number 1 is in the top left corner, with instructions 2 beneath it. The last instruction address on the left side is number 63, and then it continues on the right with number 64 to 126. With this component, I can add the third instruction to our table that I previously skipped. It is called add immediate, and it takes a value in a register, adds a number specified in the instruction to it, and then writes it back. This is the only way to input specific numbers to the CPU. Previously, I wanted to have an instruction called load immediate, which instead of adding a number, it overrides the value, but there wasn't any space left for it. But it can be replaced with two instructions: add register X, register 0, register 0, that writes 0 into desired register, and then using add immediate to set it to a wanted value. The program counter is a part of the CPU that holds a single value, an address of an instruction that is being decoded and executed. On each clock cycle, it increments by 1. But this alone wouldn't be enough to create more complex programs. Very important thing in programming is jumping, looping, and branching. Because of that, the program counter can also override its stored value with a number set by the second to last instruction in our table, jump. Jump has a 2-bit operand that specifies the condition under which it should jump, and a 7-bit operand, which is the instruction address in the program memory. When the condition operand is 00, the jump will happen always, there is no condition. Remember those two 1-bit outputs of the ALU called flags? Well, they are used in conditions. The first one is 0 flag. It will turn on when the result of an ALU computation is 0, and will stay that way until the next computation. When the condition operand is 10, the program will jump only if the 0 flag is on. And the other flag is called carry out. It will turn on when an ALU computation overflows, which means there isn't enough space in 6 bits to store the result. And so, when the condition operand is 11, the jump happens only if the carry out flag is 0. At this point, I measured how long does it take at maximum to execute one instruction and got something around 25 seconds. So I built a clock to synchronize everything. The problem was, there wasn't any way to stop the program without doing it manually, and I didn't want to add another instruction just because of that. Instead, I used the very last address of program memory, 127, and made it so that whenever the program counter counts up or jumps to this address, it will stop the clock. Also, in instruction sets, there usually is an instruction called no op, or no operation, which does nothing and is basically an empty instruction. And to save space, I didn't include it. Instead, when you leave an address in program memory full of zeros, it translates to add register 0, register 0, register 0, which adds two zeros together and tries to write them to register 0, which is not possible, so it does nothing. When planning the CPU architecture, I talked about the other type of memory, RAM, which has bigger capacity than registers, but it cannot be used directly in computations. That was the last major component of the computer I built. It has 64 addresses, and I managed to make it pretty much the same size as the registers, because I changed the wiring. In registers, there are a lot of redstone intersections happening all over the place, but in RAM, the repeaters that store information are in between the wires, which are used both for reading and writing. Looking back at it, I think I could have made the register smaller, but why change it when it works? With RAM comes the last instruction in our table, memory operation. The first operand is a register address, where it reads the data from or writes to. The next bit specifies if it is reading or writing. The last 3 bits are another register address, but this time the value in that register serves as a pointer to a RAM address. This may seem a bit weird, why not just specify the RAM address directly, but trust me, this is a lot more useful because you can dynamically change the pointer, and that allows to work with much larger datasets without the need to manually change the program. I still had 2 bits left, so I made them the offset. It is a number that gets added to the pointer, and can be used when doing multiple memory operations in quick succession, without the need to change the pointer with another instruction. And with that, the computer was almost done. The only thing missing was a way to communicate with the computer in more human way, using I/O or input-output devices. I decided to make 2 of each, for the output devices a pixel display and notebook speakers, and for the input devices a controller and RNG or random number generator, which isn't really an input device, but it is really useful. There are 2 ways to implement I/O in computers: memory mapped I/O and port-based I/O. Port-based I/O needs adding more instructions to the table, which is already full, so the only other option is memory mapped I/O. This means that some RAM addresses are reserved for communication with I/O and can't be used to store data. I reserved the last 5 addresses, 2 for the display and 1 for every other component. Let's start with the screen. It has a resolution 8 by 8 pixels represented by these redstone lamps. They are sadly a few blocks apart, but with the limitations I have, this is the best thing I could come up with. When I have shaders on and it is nighttime, the full image can be seen clearly. The screen has a buffer, which means whenever you plot a pixel on the display, it first gets stored in a piece of specialized memory, and only when you send an instruction to push the buffer, the whole screen gets updated with the data stored in the buffer at once. With that, you can make smooth animations and games where you don't see individual pixels changing. The display uses the memory addresses number 62 and 63. 62 is for display instructions, such as push buffer, change the color of all pixels in the buffer, and change the color of pixels plotted in the future. And the address 63 is for coordinates on the screen. The upper 3 bits are the Y coordinate, and the lower 3 bits the X coordinate. Coordinates 0, 0 are in the top left corner of the screen. When a number is sent to those addresses, the instruction is executed immediately or pixel plotted respectively. I haven't seen anyone adding notebook speakers or some other sound devices to their computers in Minecraft, so I decided to build some. These speakers can play 25 different notes with the harp instrument sounds. Whenever a number is written into memory address 61, respective note plays. To allow the player to make games or change the program while it is running, I added a simple button controller mapped to the memory address 59. Each one of those buttons corresponds to 1 bit in word and can be extracted using AND instruction. Because buttons emit a short pulse, the redstone signals are stored in the controller until the first read from that address. And the last device I made is a random number generator or RNG. The easiest way to make RNG in Minecraft is using a hopper-dropper combination, but this wasn't redstone-y enough for me, so I decided to go for a more computational option: linear feedback shift register. I slightly modified it, so it can create any 6-bit numbers, because the basic one can't. The numbers aren't truly random, they are just pseudo-random, because they are the output of some previous computations, but they are random enough to use in games or other programs. I should also mention how to make programs for this computer. I haven't created any external assembler or emulator, so every single program I made was by hand, but it is possible to make stuff like that to make it faster and easier. Just to show you how it works, I made this simple program that indefinitely increments a number in the first register by 1. I have to convert every instruction to binary and then place a redstone dust where a 1 should be. To start the program, I switch this lever, and to make it quicker I can increase the tick rate. As you can see, the number increases by 1 every couple of seconds. Because this program never stops, I have to do it manually by flicking this lever again. Then I can use these other buttons to reset the program counter, registers, RAM and I/O. Well, and what programs can it run? You will see in a showcase. I hope you enjoyed the showcase. This video took a lot of time and effort, so I would appreciate any support. You can like, subscribe or write a comment. It is also free. And with that, I wish you have a nice rest of your day. Goodbye.